SI engine. As we have discussed earlier, there is a definite flame front formed in the combustion chamber of an SI engine once the stage 1 is over. As we had discussed earlier, once the stage 1 is over, there is a definite flame front that is formed in the combustion chamber. That stage 1 is also known as ignition lag. So this flame front is propagating inside the combustion chamber. The flame front velocity shall have a definite influence on the rate of pressure rise in the combustion chamber. The rate at which the pressure is increased in the combustion chamber is greatly influenced by the velocity of the flame front propagation. The factors influencing flame speed the study of factors which affect the velocity of flame propagation is important, since the flame velocity influences the rate of pressure rise in the cylinder, and it is related to certain types of abnormal combustion that occur in spark ignition engines. The first factor is turbulence. The flame speed is quite low in non-turbulent mixtures and increases with increasing turbulence. This is mainly due to the additional physical intermingling of the burning and unburned particles at the flame front. Unburned particles at the flame front which expedites which expedites reaction by increasing the rate of contact. In fact, having more turbulence, having more mix-up is definitely increasing the flame front velocity, because there is a better intermingling of the molecules of the petrol vapor and the air, thereby enhancing the rate of reaction. The turbulence in the incoming mixture is generated during the admission of fuel air mixture through comparatively narrow sections of the intake pipe, valve openings, etc. in the suction stroke. So the turbulence is already generated, particularly during the admission when petrol vapor and air mixture is passing through the valve opening, intake pipe, etc. Next is fuel air ratio. The fuel air ratio has a very significant influence on the flame speed. The highest flame velocities are obtained with the somewhat richer mixture, that is air fuel ratio slightly lesser than 15. Number 3, temperature and pressure. Flame speed increases with an increase in intake temperature and pressure. A higher initial pressure and temperature may help to form a better homogeneous air vapor mixture, which helps in increasing the flame speed. This is because increasing pressure will increase the density of the charge. Fourth one is compression ratio. A higher compression ratio increases the pressure and temperature of the working mixture, which reduce the initial preparation phase of combustion and hence less ignition advance is needed. Higher pressures and temperatures of the compressed mixture also speed up the second phase of combustion. Thus, engines having higher compression ratios have higher flame speeds. Next parameter that would influence the flame speed is engine output. The cycle pressure increases when the engine output is increased. This results in increased flame speed. Next parameter is engine speed. The flame speed increases almost linearly with increase in engine speed. Since the increase in engine speed increases the turbulence inside the cylinder. Next, coming to the rate of pressure rise. The rate of pressure rise in an engine combustion chamber exerts a considerable influence on the peak pressure developed, the power produced, and the smoothness with which the forces are transmitted to the piston. The rate of pressure rise is mainly dependent upon the mass rate of combustion of mixture in the cylinder. Now let us draw actually the picture or the figure that shows the variation of pressure with the crank angle in a spark ignition engine. The diagram goes like this. This is the motor curve. If there is no combustion of the fuel, motoring curve. This is high rate of combustion. This is normal rate of pressure rise. This is low rate of pressure rise. You can see the peak pressures. This is pressure y-axis in bar. This is stop dead center position. This is before TDC. This is after TDC. These are the starting of pressure rises. The relationship between the pressure and the crank angle for three different rates of combustions are shown. Curve 1 is the first one, top one is the high rate of combustion. Curve 2 is the medium rate or normal rate of combustion. Curve 3 is the very low rate of combustion. We can see from the figure that with the lower rate of combustion, longer time is required for the completeness of combustion, which necessitates the initiation of burning at an early point on compression stroke. This is compression, this is power or working stroke. So with the low rate of combustion, we have to initiate the combustion at an early state, what we have seen in the motoring curve on the during compression. Also, it is seen in the figure that higher rate of pressure rise as a result of the higher rate of combustion generally produce higher peak pressures at a point closer to TDC. In fact, it is generally a desirable feature, because higher peak pressures closer to TDC produce a greater force acting on the piston through a larger part of the power stroke, and hence increase the power output of the engine. The higher rate of pressure rise causes rough running of the engine because of vibrations and jerks produced in the crankshaft rotation, and also tend to create a situation conducive to an undesirable occurrence known as knocking. So, a compromise between these opposing factors is accomplished by designing and operating the engine in such a manner that approximately one half of the pressure rise takes place by the moment the piston reaches top dead center. So, this results in the peak pressure being reasonably close to the beginning of the power stroke, yet maintaining smooth engine operation. So, the bottom line of the discussion is, if the rate of combustion or the rate of pressure rise is too low, we do not get much work output from the engine. On the other hand, if the rate of combustion or the rate of pressure rise is too high, this leads to a rough engine operation, and it may also lead to an abnormal combustion called knocking or detonation of the engine. So we have to make a compromise between these two extremes and get an optimum pressure rise, that is to get a good power, and as well as to see that the knocking or the detonation is avoided. So now let us and all this discussion, earlier discussion, is regarding to the normal combustion. Now let us discuss about abnormal combustion. In a normal combustion, The flame initiated by the spark travels across the combustion chamber in a fairly uniform manner. Under certain operating conditions, the combustion gets deviated from its normal course leading to loss of performance and possible damage to the engine. This type of combustion may be termed as an abnormal combustion. Or knocking combustion. What are the consequences of this abnormal combustion? These are loss of power, recurring pre-ignition, and mechanical damage to the engine. How do the knocking happens in the SI engines? Let us discuss this very important topic. The phenomenon of knock, which is also called detonation, in SI engines. Let us discuss about the how do the knocking happens. In SI engines, combustion which is initiated between the spark plug electrodes spreads across the combustible mixture. A definite flame front which separates the fresh mixture from the products of combustion travels from the spark plug to the other end of the combustion chamber. Heat release due to the combustion increases the temperature and consequently the pressure of the burned part of the mixture above those of the unburned mixture. So there is a pressure gradient created between the burnt gases and the unburned mixture. In order to effect pressure equalization, the burned part of the mixture will expand. And compress the unburned mixture adiabatically, thereby increasing its pressure and temperature. This process continues as the flame front advances through the mixture. And the temperature and pressure of the unburned mixture are increased further. If the temperature of the unburned mixture exceeds the self-ignition temperature of the fuel, and remains at or above this temperature during the period of pre-flame reactions, which is also called as ignition delay, spontaneous ignition or auto ignition occurs at various pinpoint locations. This phenomenon is called knocking. The process of auto ignition leads to knock. The phenomenon of knocking could be understood by looking at this figure. This is the ignition, this point. Referring to the figure which shows the cross section of the combustion chamber with the flame advancing from the spark plug location A, this is a spark plug location, without knock. Whereas the next figure, what I am going to draw now, shall show that flame front propagation compression, this is power stroke, this is the point where ignition is given. This violent and erratic pressure pulsations or vibrations of gaseous products is called knocking. TDC, BDC, TDC. In the normal combustion, the flame travels across the combustion chamber from A towards D. The advancing flame front compresses the end charge. End charge, please note that the main actor in the phenomenon of detonation or knocking in the spark ignition engine is the last portion of the unburnt charge. The advancing flame front compresses the end charge B''D, farthest from the spark plug. Farthest, please note that farthest, at the farthest location from the spark plug, thus rising its temperature. The temperature is also increased due to heat transfer from the hot advancing flame front. Also, some pre-flame oxidation may take place in the end charge, leading to further increase in temperature. In spite of all these factors, if the temperature of the end charge had not reached its self-ignition temperature, the charge would not auto-ignite and the flame will advance further and consume the charge B'(D). This is a normal combustion process which is illustrated in the figure 1. In the normal combustion process, as the flame front is advancing from A to D, the last portion is unburned charge, which is shown with the dotted lines, is compressed. If it does not reach the self-ignition temperature, in spite of all the above reasons, there is no chance for detonation or knocking. However, if the end charge B'(D) reaches its auto-ignition temperature and remains for some length of time equal to the time of pre-flame reactions, the charge will auto-ignite, leading to knocking combustion. In the figure 2, it is assumed that when the flame has reached the point B', the charge ahead of it has reached the critical auto-ignition temperature. During the pre-flame reaction period, if the flame front could move from B' to only C', then the charge ahead of C' would auto-ignite. This is the charge ahead of C'. This particular charge would auto-ignite due to the self-ignition, to the temperature reaching the self-ignition temperature and the ignition delay of this portion of the C' charge was complete. Because of auto-ignition, another flame front starts traveling in the opposite direction to the main flame front. When the two flame fronts collide, a severe pressure pulse is generated. The gas in the chamber is alternatively compressed and expanded by the pressure pulse until pressure equilibrium is restored. This disturbance can force the walls of the combustion chamber to vibrate at the same frequency as the gas. Gas vibration can be gas vibration frequency is in the order of 5,000 cycles per second, which is shown in the figure also. The violent erratic pressure variations could lie in the range of 5,000 cycles per second. So the knocking should be avoided at any cost by varying certain factors. Now let us discuss about what are the various engine variables that could affect the knocking phenomenon in the SI engines. Effect of engine variables on knock. Density factors. Any factor in the design or operation of the engine which tends to reduce the temperature of the unbound charge automatically reduces the possibility or the tendency of knocking by reducing the temperature of the end charge. For auto ignition. Similarly, any factor which reduces density of the charge tends to reduce knocking by providing lower energy release. For example, taking the compression ratio, compression ratio of an engine is the most important factor which determines both the pressure and temperature at the beginning of the combustion process. So, increase in compression ratio increases the pressure and temperature of the gases at the end of the compression stroke. This decreases the delay period of the end gas and thereby increasing the tendency for knocking. What is the delay period? The last portion of the unburned charge after reaching the critical temperature conducive for the auto ignition, it should stay there for a definite amount of time to auto ignite. This period is called as the delay period. So, increasing compression ratio decreases the delay period of the end gas or the end charge and thereby increases the tendency for knocking. Increase in compression ratio increases the pressure and temperature of the gases at the end of the compression stroke, which in turn decreases the delay period of the end gas and thereby increasing the tendency for knocking. The overall increase in the density of the charge due to higher compression ratios increases the pre-flame reactions in the end charge, thereby increasing the knocking tendency of the engine. So that is it is the main reason for limiting the compression to compression ratio. It's the main reason for limiting the compression ratio of an SA engine to a lower value as compared to the CA engines. Second factor is mass of inducted charge. A reduction in the mass of the inducted charge into the cylinder of an engine by throttling or by reducing the amount of supercharging or by reducing the amount of supercharging reduces both temperature and the density of the charge. At the time of ignition. This decreases the tendency of knocking. Next parameter is inlet temperature of mixture. Increase in the inlet temperature of the mixture makes the compression temperatures higher and thereby increases the tendency for the knocking. Hence, a lower inlet temperature is always preferable to reduce knocking. A lower inlet temperature of the mixture is always preferable to reduce knocking. Next parameter is temperature of the combustion chamber walls. Temperature of the combustion chamber walls play a predominant role in knocking. In order to prevent knocking, the hot spots in the combustion chamber should be avoided. In order to prevent knocking, the hot spots in the combustion chamber should be avoided. That means the combustion chamber walls must be properly cooled. Next point is retarding the spark timing. By retarding spark timing, from the optimized timing, that is having the spark closer to TDC, the peak pressures are reached farther down the power stroke and are thus of lower magnitude. So by retarding the spark, that is by giving the spark closer to TDC, the peak pressures are reached farther down on the power stroke and thus of lower magnitude because there is a more volume available. This might reduce the knocking. So peak pressures are reached farther down on the power stroke and thus are of lower magnitude. This might reduce knocking. Last parameter is power output of the engine. A decrease in the output of engine decreases the temperature of the cylinder and the combustion chamber walls. And also the pressure of charge, thereby lowering mixture and end gas temperatures. This reduces the tendency of knock.